Representation of noise in circuits. Consider a general circuit with one input port and one output port. Figure. How do we quantify the effect of noise here? The natural approach would be to set the input to 0 and calculate the total noise at the output. Total noise at the output due to various sources of noise in the circuit. This is indeed how the noise is measured in the laboratory or in simulations. Here you can see the figure noise sources in a circuit. While intuitively appealing, the output referred noise does not allow a fair comparison of the performance of different circuits because it depends on the gain. For example, as depicted in figure, if a common source stage is followed by a noiseless amplifier having a voltage gain A1, then the output noise is equal to the representation in equation multiplied by A1 square. Here you can see the figure addition of gain stage to a CS stage. Considering only the output noise, we may conclude that as A1 increases, the circuit becomes noisier, an incorrect result because a larger A1 also provides a proportionally higher signal level at the output. That is, the output signal to noise ratio SNR does not depend on A1. To overcome the above quantity, we usually specify the input referred noise of circuits illustrated conceptually in figure. The idea is to represent the effect of all noise sources in the circuit by a single source. Vn square n square bar at the input such that the output noise. Here you can see the figure determination of input referred noise voltage. In figure B equals that in figure A. If the voltage gain is AV, then we must have Vn out square bar is equal to AV square Vn square Vn in square bar. That is the input referred noise voltage that in this simple case is given by the output noise voltage divided by the gain. At this point of our study, we make two observations. First, the input referred noise and the input signal are both multiplied by the gain as they are processed by the circuit. Thus, the input referred noise indicates how much the input signal is corrupted by the circuit's noise. That is how small an input the circuit can detect with acceptable SNR. For this reason, input referred noise allows a fair comparison of different circuits. Second, the input referred noise is a fictitious quantity in that it cannot be measured at the input of the circuit. The two circuits of figures A and B are mathematically equivalent, but the physical circuit is still in that figure A. In ongoing In the foregoing discussion, we have assumed that the input refer noise can be modeled by a single voltage source in series with the input. This is generally an incomplete representation if the circuit has a finite input impedance and is driven by a finite source impedance. To understand why, consider the common source stage of figure A, where the input capacitance is denoted by Cin, and 1 by F noise is neglected for simplicity from equation. The input referred noise voltage of the circuit is given by 8 kT by 3 gm plus 4 kT by gm square Rd. Now suppose the preceding stage is modeled by the Thevenin equivalent having an inductive output impedance. Figure B, simplifying the circuit for noise calculation, is shown in figure C. We seek to find the output noise as L1 increases owing to the voltage division between L1s and 1 by Cn as the effect of V in square in bar at the gate of M1, and hence at the output vanishes as L1 approaches infinity. The result, however, is incorrect because the output noise of the circuit is equal to 8 kT by 3 gm Rd square plus 4 kT Rd and independent of L1 and Cn. Here you can see the figure CS stage including input capacitance, B CS stage simulated by a finite source impedance, C effect of the single stage source. Let us summarize the problem. If the circuit has finite input impedance, modeling the input refer noise by merely a voltage source implies that the output noise vanishes as the source impedance becomes large. An incorrect conclusion. To resolve this issue, we model the input refer noise by both a series voltage source and a parallel current source figure so that if the output impedance of the preceding stage assumes larger values, thereby reducing the effect of V in square bar in, the noise current source still flows through a finite impedance producing noise at the input. It can be proved that V in square in and in square in bar are necessary and sufficient to represent the noise of any linear two-port circuit. Here you can see the figure representation of noise by voltage current sources. How do we calculate VV if Vn square in bar and in square in bar? Since the model is valid for any source impedance, we consider two extreme cases, 0 and infinite source impedance as shown in figure A. If the source impedance is 0, In square In bar flows through Vn square bar In and has no effect on the output. Thus the output noise measured in this case arises solely from Vn square In bar. Similarly, if the output is open, figure B, then Vn square In bar has no effect on the output noise is due to the only In square In bar. Let us apply this method to circuit of the figure. Here you can See the figure, calculation of input, refer noise, A voltage and B current. The reader may wonder if both the reader may wonder if the use of both voltage source and a current source to represent the input refer noise counts to the noise twice. We utilize the circuit of figure as an example to demonstrate that is not so. Considering the environment depicted in figure, we prove that the output noise is correct for any source impedance Zn, assuming Zs is noise. Here you can see the figure. CS stage simulated by a source impedance is less. For simplicity, we first calculate the total noise voltage and the gate of M1 due to Vn square In bar and In square In bar. How is the voltage obtained? By superposition of voltages of powers. The two forces Vn In square bar and In square In bar is are generally correlated simply because they may represent the same two noise mechanisms in the circuits. In fact, equations can be represented as Vn equals to Vnm1 plus 1 by GMRD Vnrd In is equal to Cn as Vnm1 plus Cn S by GMRD Vnrd, where Vnm1 denotes the gate refer noise voltage of M1 and Vnrd the noise voltage of Rd. We recognize that Vnm1 and Vnrd appear both Vn and In in creating strong correlation between the two. Thus, calculation must use superposition of voltages as if Vn and In Vn in and In are deterministic quantities adding contributions to Vn and In. At the S in figure, we have Vnx equal to Vns equal to Vn in 1 by C in S by 1 by C in S plus Zs plus in Zs by C in S by 1 plus C in S plus Zs is equal to Vn plus in Zx plus Zs by Zx Cns plus 1. Substituting for Vn and In from equation representing we had Ins equal to 1 by Zs Cns plus 1 into Vn M1 plus 1 by GMRD Vn Rd plus Cns Zs Vn M1 plus 1 by GMRD plus into Vn Rd V is equals to Vn M1 plus 1 by GMRD Vn Rd. Note that Vns is independent of Zs and Cn. It flows a Vn square out bar is equal to Gm square Rd square Vn square Vn square Vn square S bar is equal to 4 kt 2 by 3 Gm plus 1 by Rd into Rd square, same as equation. Thank you.